Good morning and welcome. A couple of things before we dive into the bulk of the content. Firstly, I just want to quickly thank Canonical, my employer, for making it possible for me to be here this week. It's certainly a great conference, a lot of interesting speakers. Actually get to be here and attend is great. The other thing is, I just want to give you a little bit of a high level as to my approach to this talk. Now, security vulnerabilities in their own, and even subsets of security vulnerabilities, we could spend an entire presentation just talking about those, and particularly one of. We could also spend an entire talk, and there are entire talks, talking about specific security vulnerability mitigations. So I'm not going to do that. My goal is basically to give you a high level overview as to what, to at least start with, what we mean by security vulnerabilities. And the same with doing a fairly high-level overview of a bunch of mitigations that exist for these things. So we're effectively going for breadth rather than depth. So to make sure we're all on the same page, to start with, what are security vulnerabilities? Basically, we mean that something has gone wrong. It's a design or implementation flaw that exists in software and allows it to be manipulated in such a way that it misbehaves to the benefit of an attacker. So in this case, we have a piece of software, an attacker is interested in being mischievous, making something bend, twist it and break it to their own advantage. And that can mean a range of different things. But in the severe case, we're going to result in the Holy Grail, which is remote code execution or RCE. So in this case, I can take a machine somewhere else and basically get it to run whatever code I want it to run. Or it can be things like privilege escalation. So suddenly I've got code running as UID 0 or as root when it shouldn't actually be doing that. But there's a pile of different classes. So we could, again, spend a whole bunch of time talking about things like race conditions, symlink related problems. We could talk about buffer overflows. We can talk about a whole bunch of things. I'm going to generally stick to a couple of groups. So what do we mean by security vulnerability mitigations? What we mean is something that basically makes it harder to exploit one of these security vulnerabilities. It's a technique. They don't have to be 100% perfect. We just have to up the level, make it a little bit harder in some particular way. Ideally, we can have a bunch of complementary mitigations. So we can have things which make it harder in one direction. We can make something which makes it harder in a different direction. And then we can use these together. And particularly if we pick a pair that happen to essentially overlap or provide complementary functionality, and we can end up with something which is a near complete solution. And ideally, they'll have minimal or low overhead. We could certainly add there are a lot of mitigations around where we can make things really difficult, but the cost of doing so is prohibitively expensive. So again, we're looking for things that not only raise the bar and make it harder, but hopefully are also relatively cheap. So at the end of the day, what are we trying to achieve? Well, we want to make security vulnerabilities impractical to exploit in the real world. As has been a common theme this week, software is bug-free. Software is full of bugs. Human beings aren't great at writing software that doesn't have errors in it, whether that be design flaws, implementation flaws, things that they didn't, corner conditions that they didn't expect. So we're always going to have security vulnerabilities of some sort. But if we can take security vulnerabilities which exist, but an attacker isn't actually able to usefully exploit those to gain RCE or raise privileges, then we've effectively achieved our job. So we've basically blocked or thwarted the attack. At the end of the day, whilst the bug exists, we've got time to fix it, to patch it, to deal with it, and we don't have problems which would otherwise occur. Again, we're looking to raise the bar through multiple mitigations. We're not looking for a silver bullet. And one thing which is quite important in this field, we want to fail closed. If something goes wrong and we aren't sure about it, we basically want to stop, shut things down. In the case of failing closed, we actually find bugs. People are aware that bugs exist, they get fixed, and obviously we avoid having that particular vulnerability again. A lot of the vulnerability mitigations which I'm going to talk about, it's sort of an interesting thing. a lot of the earlier ones, which I'll cover, are certainly in these days, a lot of different operating systems, but a lot have also come out of a particular project called the OpenBSD project. The OpenBSD project is a fully usable, secure by default operating system, so it's kernel and userland. Happens to also be the home to many other software projects, including things like LibreSSL, OpenNTPD, OpenSMTPD. Some of you probably have heard of OpenSSH and tmux. Yeah, a few small things. But the interesting part as far as this talk is concerned is it's effectively a research and development playground, especially when it comes to security and security vulnerability mitigations. So a lot of the things that I'm going to be talking about either exist in OpenBSD or have at some point started there and ended up in lots of other places. The other thing which I'll certainly note is that a lot of the mitigations that are in OpenBSD aren't necessarily OpenBSD inventions. There are certainly a lot that are. A lot of things have actually come up as ideas in other fields, in other research papers presented by other people, but they've actually been implemented in OpenBSD very early on and effectively tested and investigated there. So before we get into this a little bit further, just, I'm guessing there's people here from a lot of different backgrounds, a lot of different experience, a lot of different levels of knowledge. So make sure everyone's on the same page. I just want a quick revisit over CPUs and stacks. One of the functions, or one of the instructions that a CPU will traditionally provide is a way for calling functions. Strangely, this is often called call, for example. And what this will do is it will push the current instruction pointer onto the stack so that we know where we're coming from and we can come back to it. It then changes the instruction pointer to something that we say, hey, we want to call this particular function, and we go off and we start executing this new piece of code. They also provide instructions for undoing this. So we can go from saying, okay, we want to call into a function, now we want to actually return from the function. The return will effectively pop the return instruction pointer off the stack, and we go back to the code that we were previously running, and we resume execution there. This is very useful. It means that we can write code that actually, we can call a function, we can obviously do some processing, come back to it. And we can have a function which calls another function, which calls another function, we can bounce back out of multiple layers. But the interesting thing is that we have data that we're effectively storing. So we have what we call a stack frame. At the bare minimum, the interesting part is that this contains the return address or the return instruction pointer value. This is in memory. So pretty much in the early days, most of the attacks centered around buffer overflows. And this was basically using some sort of technique, we'll find a way that we could actually overwrite the return instruction pointer on the stack. Quite often, this is due to incorrect or missing bounds checks. A lot of these were due to bad or poor or very difficult to use correctly APIs, and this still exists somewhat today. And in addition to overriding the return instruction pointer, usually the goal was to supply some sort of shell code that this would return to. And so we would take something which would simply overwrite bounds, would provide some interesting information, including the return instruction pointer, a chunk of shell code, and lo and behold, we have a shell. Or whatever other thing we want to exploit. One of the infamous papers on this was published in FRAC back in '96 called Smashing the Stack for Fun and Profit. If you haven't read it, a lot of good reading. So we can have some code like this. If you don't understand C, hopefully it's relatively easy to follow along. But we're basically allocating a buffer of 256 bytes. We put a long string value in it. We null terminate it, which is what C uses for strings. And then we call into some function. Now, this function happens to have declared a buffer with 16 bytes. The people who have had coffee this morning will note that 256 is somewhat larger than 16. And lo and behold, we then call a function called strcpy or STL Copy. And we're saying basically copy this string over from one location to another. Now, of course, this is going to simply run off the end. So we're going to have lots of A's that we've put in the long string, And once we get past 16 bytes of buffer, we simply keep writing over memory that we're not supposed to touch. Incidentally, buffer here is a stack variable. So it's placed buffer on the stack, we've overwritten part of the stack, we've then potentially overwritten the return instruction pointer, things go wrong, and it goes downhill from here. There's a bunch of ways that we can and we have mitigated this. So these types of attacks, one way of mitigating them or preventing them is via a thing called WriteX or execute. And the whole concept here is that we mark memory regions as being either writable or executable, but not both. And so what this means is in a previous example where we'd simply overwrite the return pointer and we'd point it to shellcode or memory that we'd supplied which we wanted to execute, this no longer works. We can certainly still overwrite the buffer, we can crash the program, we can have it do weird things, but we can't actually get it to execute code that we've actually provided to it. And this is a big win. Unfortunately, this is not a solved problem. There is still code that exists today. WriteX or execute's been around for a long time, but there's still code that today exists which actually requires write and execute permissions. Most of this exists in JITs, or a lot of it exists in JITs, particularly in very large browsers, and of course these are completely secure and not interesting attack surfaces to anyone. On OpenBSD, the solution generally to this has been that we disable write and execute can't be enabled together unless a binary is marked with a WX needed flag, which is a linker flag, basically adds a elf section to it that says, hey, this thing actually does require this, so you've actually tell it that at compile time. And it also has to be on a file system which has been mounted with WX allowed. So we make this as hard as possible. But if you go and install certain pieces of software from ports or packages, then you can still actually get it to work because it depends on this stuff. If you're in a position to actually address some of these, please do. Another way that we can mitigate buffer overflows is via address trace layout randomization, or ASLR. And so what this does is whenever we start a process, we place code, data, and stack at randomly selected locations. The upside here is that every single execution of a program should result in a different layout. If you know exactly where everything's going to be placed in memory, it makes it incredibly easy to write a buffer overflow. I had third-year university students do it in a very short time span. It doesn't take them long to teach them and for them to learn this, and they can figure out how to do it. But as soon as you start moving things around and it's no longer at fixed locations, it makes it a lot harder. We have to actually figure out what the return instruction pointer would be. We have to figure out where the code's actually going to be placed in memory. In other words, we now actually have to gain information about the process in order to actually implement the exploit. We've raised the bar. Another way that is, or another technique that's used to mitigate buffer overflows is via a thing called stack protector. One of the early implementations of this was a thing called ProPolice. And basically the idea here is that we have a stack canary. So in addition to pushing the return address onto the stack, we put some value here. And basically what happens is if you've been attacked via a buffer overflow and the return address has been overwritten, chances are they've also overwritten the stack canary. So during the function epilogue, when we're returning from a function, we simply check to make sure that the stack canary is intact. If it's intact, then we infer that the return instruction pointer hasn't been overwritten and we continue on our merry way. Again, this can catch and prevent a large number of common attacks that we would be interested in preventing. But you can work around it. If you can identify the per object value that's been written to all these functions, then obviously you can write it there yourself. Perfect sense. Or you can possibly avoid overriding it, in which case, it's a non-issue either way. But again, we've raised the bar. Enter the new era. So these days, we're more interested in things like return-oriented programming or ROP. Most of the trivial attacks via things like buffer overflows have been addressed in various ways that we just mentioned, but this is interesting. The whole idea here is that we now provide our own sequence of stack frames. So we have a series of stack frames. Each of these frames is obviously a return address on the stack, and we put these together to form what we call a ROP chain. In essence, what a ROP chain is effectively addresses that will points in memory that we want to return and execute code from. We've probably got a little bit of data mixed in as well. And we do something to change the stack pointer to refer to this sequence. We return to the chain, and basically we start, we pull an address off this chain, we start execution. Each address in the stack frame list or in the ROP chain refers to what they call a ROP gadget. And this is simply a piece of code which provides some sort of functionality. It might be an addition, might be a subtraction, might be a way to call a function, perform a system call. And the easiest form of these is on the tail of an existing function, what they call an aligned gadget. So what we do here is we simply jump into the function midway through. So rather than actually jumping into the start of the function and running all the function code, we find a little bit of code at the end of a function which basically increments a register or does something interesting, and we can jump straight into that point. So now we've got something which can do an addition or a subtraction. And we can basically take these together and build up something which becomes much more complex, much more interesting. Due to CISC and variable length CPU instructions, there's also lots of interesting ways that we can do it with unintended instruction sequences. So these are referred to as polymorphic gadgets or polyret. And in this case, rather than actually jumping into the tail of a function, we're actually jumping into some location in memory which happens to contain the sequence of bytes that we need to actually run a particular set of instructions, but that's not what the compiler or the author of the code actually intended. So we can actually analyze a binary, we can pick out a sequence of bytes, and we can simply take that and run it. There's a whole set of tools around this stuff. Basically, you can say, hey, go and analyze this binary, analyze this library, and it will identify a list of gadgets that are available. If we get a basic set of gadgets, we can generate chains. We can do things like, hey, give me a set of stack frames which will actually pop a shell. The really interesting thing is this happens to render WriteX or execute largely ineffective. We don't actually have to have execute. All we're doing is providing data. So we can write to memory, we can provide a ROP chain, we can then have the CPU execute the code that's already in the program. So, as I mentioned before, we simply have a whole bunch of return addresses, possibly some data mixed in, depending on what we're doing, and we go from there. But it gets even better. So the original ROP paper, or one of the more interesting original ROP papers, was a thing called When Good Instructions Go Bad. This is published by the University of California, San Diego in 2008. This was a follow-up in 2014 which came out of Stanford. And basically the interesting thing here is that we no longer need access to the binaries to actually build the ROP chains. All we need is to find an existing stack overflow or buffer overflow, and we need a service which happens to restart itself whenever it crashes. Of course, no one would do this. Doing this, we can remotely construct a gadget which allows us to call the write system call. We can call the write system call, we can get it to basically give us the contents of the process memory, and lo and behold, we now have a binary that we can run through normal standard analysis to give us a ROP chain. We now attack it via that ROP chain, we can basically get it to do whatever. The interesting thing here is the paper called Hacking Blind basically demonstrates ways that they attacked both toy services, but also things like Nginx and MySQL to basically get hold of the process without actually knowing what was running and build up a ROP chain and go from there. So how can we mitigate ROP? One approach that's used in OpenBSD is a thing called Mapstack, and this is basically a memmap flag which marks a memory region as being stack memory. Whenever we enter into or exit from the kernel, and then we check the stack pointer and make sure that it happens to actually lie within one of these regions which is marked as stack memory. So this means that if you happen to provide it with a ROP chain which was placed into memory in a location which happened to not be stack, then we will simply terminate the program and have a nice day. But it does require, it can be worked around if an attacker is able to call mmap with Mapstack. Again, it's not a silver bullet or 100% solution, but it does make things harder. One of the other interesting things which has been added is basically an extension to Stack Protector, or a better version of the Stack Protector, a thing called retguard. So remember before we were talking about the fact that if we're using align gadgets, we're basically looking to jump into the tail of an existing function and return back. Obviously, in the case of a Stack Protector, that's fine because we still check the stack canary. We can put the known stack canary on there if we can gain access to it. Still makes life harder. But with retguard, we're actually computing and storing a cookie based on the return address on the function entry. So we take a randomized value which is provided on a per function basis. We do a calculation, we store it, we then compare it on exit, and we actually verifying that the return address is what we actually intend it to be when we called the function. Again, this makes it a lot harder to actually do anything useful here. Another challenge with ROP is that we have what's known as NOP sleds, which are basically a series of NOP instructions that are typically used for text alignment. And if we have NOP sleds, then an attacker can be sloppy. We don't actually have to jump straight into a piece of code at that exact instruction. We can jump in where the NOPs are, and we'll just simply keep executing NOP operations or instructions until we actually reach the code that we really wanted to execute, and we can go from there. Another thing that was done was we basically took the compiler generating NOP sleds, and particularly where they were located in manual assembly, and they were converted to basically being a jump instruction at the beginning of that sequence followed by a whole bunch of int3s, which now means that you either have to land right on the jump instruction itself or at the jump target. Landing in the middle is no longer interesting to you. Int3 happens to be a debug trap instruction, so if you happen to land on one of these, things don't work so well. And there's a lot of work done to reduce the number of gadgets that were available. So part of this, a lot of this work was done by a guy called Todd Mortimer, who's done a bunch of work on the GCC and Clang compilers available in OpenBSD, and looked at things like, okay, we can actually change the code that's being generated. One of the interesting things with CISC and modern CPUs, we generally have a lot of different ways of doing the same thing, and we also have selection over what registers we're actually using to do it. If we use certain registers, we end up with certain instructions which are interesting from a ROP perspective, particularly the ret instruction, which happens to be a polyret. We can simply change the code that's coming out of the compiler. We can say, okay, instead of using that particular register, use this one instead. Suddenly we've taken a polyret that could be used for a ROP attack, no longer exists. And likewise, there's a fix-up module in Clang which goes through and basically does some of this work. Interestingly, the ARM64 kernel on OpenBSD is gadget-free. ARM64 is using fixed width instructions. There's no polymorphic rets to deal with to start with, and the use of retguard protects all of the other return cases. But while that might be the end goal, and if we like the silver bullet, it's not necessarily essential. So on AMD 64, we have a significantly reduced attack surface. When the same work was done, whilst we can't say we don't have any gadgets available in the kernel that you can use, the same work means that if we can reduce the diversity of gadgets that is available, then it becomes much, much harder to build ROP chains. And one example of this was running one of the standard ROP analysis and chain building tools against libc. After some of this work was done, previously it could go through and find 8,000–9,000 gadgets, and we could easily build some code or a chain that would pop a shell. Once the work was done and we're compiling with things like retguard and removing polyrets, all of a sudden the same tooling can't find enough gadgets to actually achieve the same thing. So again, we're raising the bar. The following mitigations are interesting because they are general approaches rather than targeting specific vulnerabilities. So some time ago, privdop was a thing and got added to a number of functionality, particularly on OpenBSD. The whole idea here is that we drop privileges as soon as possible. Now, if we take a typical program, we're going to normally need to do some sort of setup. We might need to open a raw socket, but after that, we no longer need root privileges to run. So if we change from running as root to running as a less privileged or non-privileged user, then if we happen to manage to exploit, for example, a buffer overflow in it, then it's no longer as useful as it would have been previously. We can't run code as root. Hopefully that means we can't write shell kits to the system and those sorts of things. So TCP dump was an example of this. We switched to non-privileged user before we actually start parsing packets. Now, even as late as 2017, there were parsing flaws in TCP dump, which would basically mean that if you had the ability to put certain traffic on the network, someone running TCP dump as root on a machine, you have RCE as root. Not what you want. Privcep's an even more interesting approach to this. So we take a program that provides some sort of functionality and we split it up into separate processes. Each of those have different privileges. Each of these processes then communicates via some form of restricted IPC. Common techniques are things like socket pairs on OpenBSD. It's very common to use a thing called iMessage, which is basically message passing over sockets. And it means that part of the program can retain privilege whilst the others do not. And we then can ask the other program to do something on our behalf, check something on our behalf. If the part that doesn't have privilege gets attacked, it's not actually useful. How many of you run a not very well-known piece of software on your servers called SSHD? A few of you, okay. There's a very interesting situation with SSH in 2002. There's an integer overflow bug which basically meant you could attack this thing and exploit it severely. Just before this, SSH had been rewritten to use, or to at least support Privcep. So rather than running everything as root, the pre-authentication code, so effectively the piece which talks to the network before it actually even knows who you are, now runs as a less privileged or non-privileged user. We still have to do things like check authentication. So we need access to the system. We have to, at some point, potentially, if you do authenticate, switch to your user ID and actually let you log in as you. So we still obviously have to have privileges to do this. But we don't have to run the network-facing part, which is attackable and requires no authentication as root. When this integer overflow became known, the solution to the problem was, well, part of it was, if you're running the Privcep code enabled, it's not actually exploitable. OpenBSD had this. It was basically advised to, obviously as soon as we published, they published details of this particular attack, then everyone's system running SSHD is vulnerable to it. Or likewise, if they put up a patch and say, here, go patch your code, there's going to be a window, they could turn this around and simply say, okay, grab the most recent code, enable Privcep, and you'll be fine. And these days, I believe that the non-Privcep version has actually been stripped out and you have to run it in Privcep mode. Again, it's not the first piece of software to do this. There were things like postfix and similar that were written in QMAR, which would use similar models a long time ago, but on OpenBSD it's common or almost standard. Another one is fork and execute or re-exec. So remember we talked about ASLR earlier. We also talked about BROP and the fact that if you have a process which, something like Nginx, which is forking processes to serve incoming requests and happens to crash, well, it simply forks off another one and execs again. If you actually have exec or re-exec as part of the process of actually switching, changing to another set of functionality, again, you're actually ending up with some new layout thanks to the execution part. So this means that we place things in different areas of memory. Again, these attacks become a lot harder because something which worked previously doesn't actually work now. A more recent one, in order to avoid having kernel information or code placed always in the same place, the kernel's now shipped as a link kit. So Basically, at installation time and again at each boot, the kernel is relinked with a randomized layout, and this means that every single OpenBSD host happens to be running a unique kernel. If you want to attack that machine, you actually have to work out how to target that particular layout, which means you have to know what the layout is. And so again, this requires discovery, which adds yet another barrier. And the same thing's also been done for libraries. So at boot time, libc, libcrypto, and ld.so, which all happen to be fairly large attack surfaces, happen to be relinked with randomized layouts. Again, building a ROP chain on your system or on someone else's system doesn't mean that it's actually going to work everywhere else. Pledge is one which is relatively new and has been a rather interesting journey to follow along. The whole idea here is that it provides restrictions based on subsets of system calls. This isn't new. There's a bunch of other tools around that do this, everything from SE Linux, AppArmor, Capsicum, etc. But the interesting thing with Pledge is it's actually a specification which is baked directly into the program. So the program is saying, I'm only going to use the following, and if it doesn't obey to that, then it simply is terminated. It can continue on further to relinquish subsets of functionality, but we can't actually regain them. It's a fairly straightforward thing to learn, easy to implement, easy to test. If you happen to say, I'm promising that I'm not going to write files, and you do, your program terminates. The really interesting thing with Pledge, though, was what happened when it was actually being rolled out to all of the system utilities. We talked earlier about the fact that we could do things like privdrop, or we could say, hey, this particular program, ping, for example, needs access to a particular piece of functionality, but if you do that externally, you pretty much have to retain that for the entire lifetime of that process. With Pledge, we can say, hey, I need access to the internet, for example, and then we can go and run some code, and then we can say, okay, I no longer need that. So we can actually, because it's baked into the program, we're actually in a position where we can reduce it as we know how to. And this resulted in a lot of code being rewritten so that things were hoisted up. Things that needed privilege were done early on in the program so that we could then decrease the amount of privilege. If we combine this with privsep, we end up with something which is basically one side has privileges to talk to the network, another process simply doesn't have any access to anything other than standard I/O, so it can potentially read and write from an existing file descriptor, but it can't actually do any more than that. So things like TCP dump or other pieces of code which happen to need to do parsing or computation, we can severely limit what they're capable of doing. Unveil's a more recent piece which is essentially complementary to Pledge, but also highly useful in isolation. And this basically hides the visibility of file systems. So we can say, okay, go and unveil. An initial call will simply mask the file system, and then we can say, look, make this file visible or make this directory visible. And we can also say, look, make this file read-only or make this file so that we can actually write to it. When you have programs where, for example, you're specifying a file to operate on as part of the command line, we can then take that, we can use Pledge and Unveil to say, okay, yes, you still need to be able to write to files, but I'm only going to let you write to a file which is part of what you've been asked to write to. And suddenly, we can't write to other places in the system or your home directory or read your SSH keys or whatever other interesting things we might do. So we've talked about a bunch of security vulnerability mitigations. These are other considerations, things that if we can do this, it will help you as a programmer, as a person running some of this software, but they're not strictly mitigations as such. If you have secure APIs, then they are easy to use correctly, and they should be very hard to get wrong. In other words, it should be secure by default. Yes, you can say, hey, do something stupid, and if you pass in the right arguments and tell it that your buffer happens to be substantially larger than it actually is, then it's going to do the wrong thing. But by default, we shouldn't be able to do that. It should be obvious and helpful to you instead. One of the early examples of this was STL Copy. So we looked at STL Copy earlier, which simply said, hey, we can write over whatever end of the buffer we happen to be asked to overwrite of. I don't know how long the buffer is, I'll just keep copying, it's not a problem. I'll find the end of the string at some point. Might be down the end of memory, but not a problem. STL Copy turns things around and basically adds a couple of guarantees and constraints. One is you as a programmer have to tell it how big the buffer is that you're actually copying into. Secondly, it guarantees that if it returns success, it will have successfully null terminated the string. So if you say copy this string into this location and you haven't actually allocated or remembered enough room for the null byte, it will fail. So things that were previously possible in terms of bad string handling become really hard and really obvious. Jumping forward a number of years, more recently, APIs like realloc array, recalloc array, and free0 have been added. Again, one of the interesting attacks is integer overflow, multiplication overflow. So we're asked to allocate memory for some value times some value, and we don't actually check that the result is actually going to end up being able to fit in whatever size number of bits we actually have. If we do this, we can get wraparound, and that does really interesting things because we can exploit some of these, and again, if it's signed or unsigned, obviously it's got some different implications. Realloc array basically says, okay, you tell me how many of these objects you want to allocate memory for, you tell me what the size of the objects are, and I'll do the math for you. The math happens to have correct bounds checks. Then we can actually go and allocate it, right? You as a programmer no longer need to think about this. Recalloc array is a slightly different spin on this. One of the challenges as a C programmer, if you don't want to leak information into memory, basically you want to clear it before you free it or return it. And in doing so, if you use the realloc functionality, basically you don't know whether it's going to say, yes, you can use some more memory in the same location, or whether it's going to have to do a reallocation and copy your existing data across and free the old piece of memory. Now, realloc will happily do this for you. If you say, okay, I want to realloc this allocation to some larger size and it needs to go and, okay, that won't fit where it is currently, we'll make a 1 meg area over here and we'll copy it across and I'll go and free the old thing for you. That's great. But now we've got a piece of data floating around potentially in memory that we don't want there. So the constraints, or the guarantees as far as recalloc array is concerned, is not only will it avoid or do the bounds checks for you, but it will also guarantee that it's actually going to clean up after itself if it happens to need to reduce or throw away memory. We also have a thing called OwnMalloc, which is basically a hardened malloc implementation, has randomized layouts and allocations with things like chunk canaries and guard pages. You can enable junking so it will actually override on free, and this allows you to find bugs quickly so that they're fixed, which also prevents exploits. Randomness is an interesting topic, and again, one that we could spend a lot of time talking about, but a lot of the mitigation techniques mentioned, so for example, the retguard cookies require randomness, and a lot of other sensitive applications do as well. Arc4Random on OpenBSD can be used in any context, is always going to succeed. It's built on top of a thing called getEntropy, which is the system call below it. This also succeeds and does not block, which means as an application developer, you don't need to deal with failures. You don't have to go, okay, I'm running in a CH root, I happen to be missing a device node which I can't open, or hang on, I can't open it because I've run out of file descriptors, or a bunch of other interesting failure modes. I happen to be booting up and now this thing's blocked because it's waiting to give me some guarantees. These things make your life easier. So in summary, we can't necessarily eliminate security vulnerabilities. If you happen to know a way to do this, please let me know. We'll go and do it, possibly get rich together, that sounds great. But we can make them very difficult to exploit or hopefully impractical to exploit. It's always an arms race. There are new attack techniques. So since BROP, there's JROP, there's very other variants and techniques on this front. There's always going to be someone coming up with another way to bend and twist things. So we have new attack surfaces. But the thing is, if we have multiple layers of defense or defense in depth, we can take a bunch of mitigations, we can use them together, hopefully find ones that are relatively cheap to do. And whilst the software or the system may be vulnerable, we can actually make it near impossible to actually exploit. And that's what we'd like to do. So thank you. I'll certainly take a few questions, just a few pointers here if you're interested in this stuff. The OpenBSD events page has a ton of talks, so there's entire talks on Pledge, on Unveil, on a lot of this stuff. One of them there, which the ROP and related work that's in OpenBSD, as I mentioned, was largely by Todd Mortimer, who presented at EuroBSDCon. A great presentation there if you want to read through it. Paper-wise, I mentioned smashing the stack for fun and profit earlier, when good instructions go bad, and hacking blind. All very good reads if you're interested in this subject.
Thank you very much. Got a couple minutes for questions, so stick a hand in the air.
Thanks. So Unveil locks off everything and then enables access to a certain thing. So if an attacker has the right gadget or something, they could just unveil more stuff?
Right. So one of the things which I jumped over, one of the last things that you will do is call unveil with null and null. And basically what this does is you can no longer call unveil. So there is a way of locking this down, basically saying, as a program, I've finished unveiling everything that I want to unveil. Now you can actually manipulate this further.
Thank you for not using Comic Sans.
Let me fix that.
So a lot of these are quite OpenBSD specific. A lot of us here presumably use Linux. What of these kind of mitigations are available in Linux?
So a lot of the earlier ones I talked about, things like ASLR, are certainly available in not just Linux, but most operating systems. Windows calls it DEP, macOS, etc. have their own names for things. What I would say is on the tail end of things, so Pledge and Unveil, as I said, there are certain similar things in terms of things like AppArm, RSC, Linux. To me, the difficulty there is that they're applied after the fact. So if you update the piece of software, you have to know what it now needs access to. Or you have to give it access to something which it then has for the lifetime of the process, which potentially means it is more vulnerable than it should be. A lot of the ROP work, so the stack protector stuff, is available in Linux. I don't know the status in terms of what's enabled by default or not by default. But a lot of the ROP mitigations, particularly the gadget reduction, the polyret reduction stuff, could certainly easily be taken and used with Clang and GCC compilers. There's nothing which makes that particular part OpenBSD specific. Things like retguard obviously require support in predominantly the compiler, but also some of the toolchain stuff. Again, there's no reason these couldn't be ported over, should you choose to do so. So if you're interested and want this stuff, go ahead and take it and use it, please. Sure.
So a lot of these techniques you're talking about, obviously from sort of C, C++, lower level language systems.
Sure.
For those of us who work in high-level interpreted languages, is there anything we can do? Do we just have to go nag the interpreter developers to start trying to find ways of baking this stuff in, or is there anything we can do right now?
Yeah, that's an interesting question or point. I think the thing is a lot of these approaches come in from different perspectives. So a lot of the things I've talked about in terms of buffer overflow protection and various mitigations actually applied to the interpreter mean that the interpreter aspect is a lot more secure. We've recently seen bugs in Perl and other interpreters where you can actually give it bad code and have it do things. So you actually gain from the stuff that I've been talking about there. But things like system calls like Pledge, you can actually call to from script languages and other code. So if you know that you're writing scripting language which is only going to do a small subset of things, obviously you can employ these techniques, things like privdrop, privsep, but also calling Pledge and Unveil. Obviously there's a little bit of work to do that, but it's certainly possible.
That's all we have time for. Please join me once more in thanking Joel for coming.